All right. Hey, everyone. Welcome back to our series on linear algebra. So we are now in section 3.5. We skipped 3.4. That has to do with upper and lower decompositions for matrices. It's an interesting read, but it's not really, it's not something we have time to cover in our accelerated pace for our course. So we're skipping it. We're moving on to section 3.5, which is, in my opinion, one of the most important sections that we'll cover in this class. So yeah, it's a really big moment for us. I've called it subspaces of Rn. That's mostly because it's very hard to name this section. So the pattern will be that we just have like a bunch of definitions and whatever, and then we'll build up to the Rank-Nullity theorem. We'll talk about version 2 for the fundamental theorem of invertible matrices. Some really awesome results. Okay, so let's dive in. I've drawn this picture, which is meant to capture the idea that we want to talk about. This is supposed to look like a plane that goes through the origin in R3, and it's not one of the coordinate planes, right? Something that's like tilted and at a weird angle. Let me zoom in a little bit so you can see these grid lines. Okay, you still can't see them. That's okay. This is meant to, you can see them a little bit. This is meant to be describing, so all of the vectors that you see sprouting out of the origin are meant to be living inside of this plane, right? And so I've kind of drawn some grid lines to illustrate that. And what we want to notice is if I took the blue vector and the red vector anchored at the origin and added them together, I get this nice purple vector. And the observation is that the purple vector also lives inside the plane. In other words, if I take two vectors that both live inside of this plane, then and add them together, I get something that still lives inside the plane. So you might ask, is the plane two-dimensional or three-dimensional, right? Certainly from one perspective, it lives in three-dimensional space, right? And it kind of seems like it takes up all three dimensions. You need an x, a y, and a z to get there. However, every single vector that lives inside of that plane can be obtained as a linear combination of the blue and the red vectors. So in that sense, and there are only two vectors there, so in that sense, it seems like the plane could be two-dimensional. And sure enough, it's a plane, it's flat. And if you take a flat piece of paper and turn it around in three-dimensional space, as long as you don't crumple it up, isn't it still two-dimensional? It's just a question of like where the floor is, your orientation. So it's kind of a puzzle. There's a number that we should attach to it. And if intuition is telling you that that number should be 2, that like the number 2, then your intuition is probably in line with dimension theory. We are going to get there. But for now, we have to actually take a step outward a little bit. Just asking the question for a plane inside of three-dimensional space is not broad enough. So what we need is, like, for example, what about a line in three-dimensional space, or a line in two-dimensional space, or a three-dimensional hyperplane in a seven-dimensional, like R7? Yeah, it's like there's a lot more going on here. So what we need is a universal definition that captures all of these notions of planes and lines and stuff through the origin in some Rn. And that's the definition of a subspace. So okay, let me tell you what the definition actually is. A subspace of Rn is any collection of vectors, any collection S of vectors in Rn such that three properties are satisfied. Number one is that the zero vector has to be a part of that set. You can't, it has to, in other words, your space, your subspace, has to pass through the origin. Number two, if you have two vectors, this is the one that we saw with the red and the blue vectors. If you have two vectors that are inside that inside that set, then their sum must also be inside that set. And then the third one is scalar multiplication. So if you have any vector inside your set, then any scalar multiple of that vector should also be in that set. Notice the second two properties are just the qualifications for linear combinations. So in other words, all linear combinations of two vectors should be, or of any two vectors should be inside of your set, or any linear combination of any vectors, just generalizing. If you have your set S, any linear combination, which is a finite sum of scaled vectors inside of that set, if you have any linear combination of vectors inside that set, you again get a vector that's inside that set, right? So that's what it means to have a subspace. We have all the linear combinations of vectors inside of any collection of vectors inside of that set. You will have to check this on your own, but the primary example are lines and planes through the origin, say in R3 or R4. Try taking some linear combinations of some vectors inside of a plane in R3 that you know about. Okay. So we have a nice theorem coming up, which is that if you have the span of a set of vectors in Rn, that span is automatically a subspace. Okay, that's a theorem. And we're actually going to prove it. We're going to use a technique called definition chasing. You're going to love this one. So what do we have to prove? We have to prove that that the span satisfies all three of those properties. Well, let me just do the first one real quick. The zero vector is 0v1 plus 0v2 all the way up to 0vk. That is a valid linear combination of these vectors. Yeah? You want me to prove to you that the zero vector is an element of this set? Well, remember, the span of a collection of vectors is literally the set of all linear combinations of those vectors. Well, here is a linear combination of those vectors, so it's a member of the span, but it's also the zero vector, which is what we want. We need the zero vector to be in there. Okay, 2. Suppose U is like C1, V1, all the way up to CK, VK. So U will be some linear combination of these vectors, and V will be D1, V1, all the way up to DK, VK. Okay, so this will be another linear combination of those vectors. We want to show that U plus V is inside of the span. Okay, so it's going to be C1 plus V1 all the way up to CK plus VK plus D1 plus V1 all the way up to plus DK VK. Rearranging that sum and factoring out constants, it looks like this: C1 plus D1 V1 plus, all the way up to CK plus DK VK. That is a linear combination of the vectors V1 up through VK. So again, the sum is inside the span. 3, we want to show that any scalar multiple is inside of the span. Well, CU is just C times C1 V1 all the way up to CK VK, which is, by the distributive property, CC1 V1, let me put the CC1 in parentheses, plus, all the way up to CK VK. again, I just distributed the c to every single term. C is some arbitrary scalar. And then what we do is we just group the parentheses around the pairs of scalars so that we have, once again, another valid linear combination of the vectors v1 through vk. That's it. These are the three properties that we needed to satisfy in order to show that the span is a subspace. So we just had to verify that it works, and it does. Great. Let's do an example though. So the vectors. So suppose we have a collection of vectors x, y, z, where 3x is equal to y, and z is equal to negative 2y. Well, if we do that, if we well, sorry, this is written incorrectly. It should say x equals 3y. Because look, we're gonna upgrade or break the example in just a second. But for now, okay. Notice this is the equation of a plane through the origin. This is also the equation of a plane through the origin. And we're asking that the vectors x, y, and z, whatever, the vectors of that form, satisfy both equations. In other words, they are on the line of intersection of these two planes. In other words, they're vectors of the form 3y, y, and negative 2y. We just plug in. This is also known as y times 3, 1, negative 2. And notice when y equals 0, you get the 0 vector. And if you take any linear combination of vectors of this form, you get another vector of this form because you can just factor out whatever value of y that you used for each term, and then just add those y values together, and you're left with another multiple of this vector, right? On the other hand, suppose I have x equals 3y plus 1, y is equal to y, of course, and z is equal to negative 2y. Well, this is equal to the vector 1, 0, 0 plus y times this other vector. 3, 1, negative 2. Now, try to make the 0 vector out of this one. I think you're going to have a hard time because you need to use y equals negative 1/3 in order to cancel out this term, this vector in the beginning, when you add them together. But if you use any value for y which is not 0, then the second two entries are going to be non-zero. So the 0 vector is not a part of this set of vectors of this form. And so it's not, this is still the line of intersection of two planes, but that line doesn't pass through the origin because this plane doesn't pass through the origin. Okay. So, that's good so far. Now, given a matrix, this is interesting, we can construct a subspace. So we just say let A be an m by n matrix. We define the row space of A, row of A, to be the subspace of Rn spanned by the rows of A. Remember, if A is m by n, let me just draw a picture here. M by n. That means it has m rows and n columns, which means that every row of A is a row vector of length n, right? So what we do is we just take all of those row vectors. Those are all vectors in Rn, and we just take their span. That's a subspace by the previous theorem, and we give it a name to that subspace. We're running low on battery. The column space is the same, except that we just do the columns of A, right? So if A is m by n, then every column of A has m entries, which means that it's a vector in Rm, right? And so we just take its span in order to construct the column space. So this example is interesting. We just have some matrix. A is 1, 0, 3, negative 1, 1, negative 3. Apparently I read the columns first. We ask, is B equals 1, 2, 3 in the column space of A? What about is the vector 4, 5 in the row space of A? And then it asks us to describe the row space of A and the column space of A. So I'm going to do this with a couple techniques. First of all, let's look at the augmented matrix 1, 0, 3, negative 1, 1, negative 3, augmented with 1, 2, 3. If you row reduce this thing, you don't have to, well, I mean, you can row reduce it all the way. If you do, you'll get 1, 0, 0, 0, 1, 0, 3, 2, 0. But the point is, we don't have to row reduce it all the way because we just have to know, is the system consistent? If the system is consistent, then we know that B can be written as a linear combination of the columns of A. That was a theorem that we covered in chapter 2. And if the system is inconsistent, then it means that B is not a linear combination of these two columns. So that's one way to check. Another, okay, that's the way to check for 1, 2, 3 specifically. But what I want to do is describe, so let's do the row space of A, sorry, the column space, no, the row space of A. Got distracted. Now notice, if you are a vector, so the rows of A are all two-dimensional vectors. If the rows of A, if you are a vector, a two-dimensional vector that is a linear combination of the rows of A, then you should also be a linear combination of the columns of A transpose. Let me write A transpose for you. It's 1, 0, 3, negative 1, 1, negative 3. And if you're listening and not watching, that's going to sound confusing. I just did the rows first. Right? Take this thing, augment with 4, 5. I'm actually not going to augment with 4, 5. I'm going to augment with an arbitrary vector x, y. And then I'm just going to add the first row to the second row. So row 2 plus row 1. 1, 0, 3, x, and 0, 1, 0, x plus y. Then we pause. Wait a second. This system is consistent regardless of what values you have for x and y, right? In other words, and if this system is consistent, then the original one is consistent, which means, so always consistent. Which means any vectors that you put for, or any numbers that you put for x and y will automatically be in the row space of A, or the column space of A transpose. So, in other words, the row space of A literally is R2. Right? Which means that, yes, 4, 5 is in the row space of A. Of course, but also so is every other vector. So this is actually a description of the row space of A. If we were to do a description of the column space of A, right, we would have to do the same thing. We'd have to set up an equation, but instead of doing the vector 1, 2, 3 in our augmented matrix, we would have to set up the augmented matrix 1, 0, 3, negative 1, 1, negative 3, augmented with x, y, z. Then we have to row reduce this. once again, notice the first row and the last row are a copy of each other. So if I just did row 3 minus 3 row 1, I'm getting 1, -1, x, 0, 1, y, 0, 0, and then z minus 3x. And now we ask, for the column space of A, if we want to describe the column space of A, we need this system to be consistent. So in other words, z has to be equal to 3x. This is the equation of a plane in R3. And so, and it is the, that is precisely the column space of A. Okay? So these are this is how we would go about describing the row space and column space of matrix A. So this is some miscellaneous facts about, definitions and facts about different subspaces. So, for example, if A and B are row equivalent matrices, then they have the same row space. Row space of A should be row space of B. What? They should have the same row spaces, right? Row equivalent matrices should have the same row space. Okay, and the proof for this is that you can make any linear if you have two row equivalent matrices, then they both row reduce to the identity. And row reduction is a reversible process, so you can use row operations to get from one to the other. But then that means that the rows of B, for example, are linear combinations of the rows of A. Or the other way around, the rows of A are linear combinations of the rows of B. So each one's rows is in the row space of the other one, which means that taking spans, each one is in the other one's row space. So they have the same row space, right? Okay, so now we have a definition / theorem. The book presents them separately. I'm going to put them together here. So let A be an n by n matrix, and then let n be the solution set for the homogeneous system AX equals 0. Then n is a subspace of Rn, capital N, whatever. And it's important enough that we give it its own name. We call it the null space of A. And actually we denote it with null A, like that. Okay, so we have to, definition chasing. We can prove this one. Maybe we'll have to, we'll gloss over the proof of this one. But the idea is, listen, the zero vector is definitely a part of this null space. That's just saying that the homogeneous system has the trivial solution. Last I checked, that's true. If you had two solutions, if U and V satisfy AX equals 0, then AU equals 0 and AV equals 0. So you just compute A times U plus V equals AU plus AV, which is 0 plus 0, because both of them are solutions to the homogeneous system. And so, right, and then 3 is going to be the same, but just do a scalar multiple of U. So it would be A times CU, which is C times A of U, or A times U, whatever. But AU is 0 and C times 0 is 0. So same. Okay, and now I want to talk about the most important definition maybe of all time. This is called the definition of this is a basis for a subspace. So a basis for a subspace is a set of, I'll just tell you I'll read it. It's a set of linearly independent vectors that span S. I've got it in green here. You should memorize this at all costs. A basis is a linearly independent spanning set. Now, it seems like spanning set it makes sense, right? We just have a set of if you have a subspace, it seems like it makes sense to define a basis to be a set of vectors that spans that subspace. But why the linearly independent qualifier? It's because, it's very easy to construct a spanning set. You just, for example, the set of all vectors inside your subspace spans that subspace for a really dumb reason, right? But that set is way too big to do anything useful with, right? Even the set, 1, 0, 0, 1, and 1, 1. This set, that's only 3 vectors, and it spans R2. But it seems too big, right? Because this one is clearly just the sum of the first two. So it seems redundant. Yeah? Linearly independent removes the redundancy of having too many vectors. That's why we have both. And the first example that we'll see of something that's big enough to do the job, but as small as possible, right? Linearly independent spanning set. This is a very important definition. Okay. Let me give you some examples of bases. By the way, the plural for basis is bases, like easy, like a hard E sound, not bases. Because we're not talking about the singular form is not base, it's basis. So several bases. Anyway, in case you hear me saying that and you're wondering what I'm saying, anyway. Okay, so let me give you some examples of bases. The standard basis, which is we have ones in each of the entries and zeros everywhere else and enough vectors to fill it up. That is always a basis for Rn. Okay, so if you have, what I have boxed in is the standard basis for R2. If you had 1, 0, 0, 0, 1, 0, 0, 0, 1, that is the standard basis for R3 and so on, right? Okay, here's another basis for R2. It's the vectors 1, 2, and -1, 3. Notice if you take their span, you get all of R2. You can do that by taking the system where these are its columns and then augmenting with an arbitrary vector xy, and then just observing that the system is always consistent. There's no inconsistency. This is what, but also notice that this is a linearly independent set. Obviously, one vector is not a multiple of the other, so they're linearly independent. They also span the set R2, the space R2, which means that they form a basis for R2. Okay. Okay. So we're going to look at this example next. We have, we want to find a basis for this span. It's not obvious, but this vector is a linear combination of the first two. Specifically, I believe that -2 times 3, -1, 5, plus 3 times 2, 1, 3 will get you that one. 0, -5, 1, I believe. Right, that's -6 plus 6, 0. 2 plus 3 is 5. Oh, I have it backwards, don't I? 2 of that minus 3 of this. That should do it. And then 10 minus 9 is 1. Yeah, this will do it. Okay. So this one is redundant. However, neither of these two is a multiple of the other, which means that, by the way, to do what I just did, you would have to set up, right, an augmented system and row reduce to see if you get something consistent. So, okay, anyway. But notice neither of the first two is a multiple of the other, and so they together form a linearly independent set, which means that their span, the span of those first two vectors, which contains the third one, is the same as the span of all three vectors, and those two, because they're linearly independent and a spanning set, they form a basis for that span. Okay, and now we have this last example. Well, I say the last example. We want to find, so we're given a matrix A. We want to find a basis for the row space, the column space, and the null space of A. Okay, the first step will always be to row reduce. So I've gone and done that. Actually, the book has gone and done that for us. All right. Now, we want to do a basis for the row space of A. Well, notice that in particular, these rows or these matrices are row equivalent. We used row reduction to get from one to the other. Well, then the row space of A is precisely the span of, well, we can't include the zero vector. In fact, when we were talking about linear independence and linear dependence, we said that the zero vector, if it is part of a set, it'll always make that set linearly dependent, because you can always make the zero vector with a linear combination of any other collection of vectors. So, barring that one, we have now three vectors which are definitely linearly independent. And because these two matrices are row equivalent, they have the same row space. So we might as well take the span of these three vectors as the row space of A. They will be the same by the theorem that we proved earlier. So 1, 0, 1, 0, negative 1, 0, 1, 2, 0, 3, and 0, 0, 0, 1, 4. This is a linearly independent spanning set, so it's a basis. Let's go for the column space of A. So the column space of A, we have to think a little bit more carefully about. Notice that when we set up this system, the two vectors that I have circled are linear combinations of other vectors in this system. What that's saying is that they are redundant column vectors. However, we don't get a corresponding theorem about the column space of A being the same under row reduction, and in fact, it won't be. Instead, what we know is that this column and this column are redundant. And so we would have been able to make them out of the other two. I believe in fact, the same linear combinations that give rise to these columns should give rise to these columns. We can check that. 2 times this column plus 1 times that column. Well, if I have 2 times this column plus 1 times this column, I get 3, 0, 1, 6, right? So we were able to construct these columns out of linear combinations of the other columns, which means that the column space of A is the span of just the first, the second, and the fourth column of A. So 1, 2, negative 3, 4. 1, negative 1, 2, 1, and 1, 1, negative 2, 1. Lastly, we'll just take a look at the null space. So the null space of A, notice if we were to view, so this is going to be very similar. But what we're doing is we're going to view the system as a homogeneous, that we'll view this as the coefficient matrix for a system of, for a homogeneous linear system of equations, right? Well, what we're doing is exactly the same thing. We just, we view the reduced row echelon form matrix as the system of linear equations that pops out after doing Gauss-Jordan elimination. So it'll be like x1 plus x3 minus x5 equals 0. X2 plus 2x3 plus 3x5 equals 0. And x4 plus 4x5 equals 0. Okay, but each of these we can just solve for. So we have free variables, x3 and x5, right? So we can solve x1, x2, and x4 in terms of x3 and x5. When we do, we'll see that x is, well, I'll just skip to the solution. Setting s equals x3 and t equals x5. That was loud. We'll see that minus s plus t minus 2s minus 3t s minus 4t and t. This is the solution vector, which means that all linear combinations we could split it into, s times one vector plus t times another vector. I'll just write it like this. The s vector will be -1, -2, 1, 0, 0. And the t vector will be 1, -3, 0, -4, 1. Any linear combination of these two vectors will give you a vector inside the null space, right? Okay, I'm going to go and charge my iPad, and I'll get back to you momentarily. Okay, that's a little bit better. I figured we should probably keep going before we lose track of the conversation. Right. So if you notice, when we're talking about the span, the number of vectors inside of a basis, in our examples of things that were spanning R2, the number of vectors was always the same. And in fact, that's true. And we state it as a theorem and or definition. This is the intuitive definition of the dimension of a subspace. So, okay, let S be a subspace. And the theorem says that any two bases for S have the same number of vectors. In fact, we just go and call this number the dimension of S. It's the number of vectors used to form a basis for that subspace. Okay, I'm going to give you some examples of dimensions. The first two are kind of silly. The dimension of just the zero vector. Well, the thing is, the zero vector itself, even if it's the only vector in a set, it forms a linearly dependent set by convention. And so, right? And so if you take the set itself, the zero vector, which kind of corresponds to just the origin, we define the dimension of just that one vector to be 0. Strange. Okay, but beyond that, this is the one that we had before. The dimension of Rn is always n. Just do the standard basis. The standard basis for Rn, that's like 1, 0, 0, 0, 1, 0, 0, 0, 1. That basis will always, that one always has n vectors in it, and any two bases for Rn will have the same number of vectors. So notice that means that the dimension is just n. Before, we had also the example that we left off with before an awkward skip in the video. So we computed the row space, the column space, and the null space of that matrix A. And notice the dimensions, the number of vectors that we needed in order to span whatever these subspaces were 3, 3, and 2. Okay, we'll just check that real quick. Notice here's 3, and here's 2. Now, it is not a coincidence that these two are the same number, nor is it a coincidence that the sum of these two numbers is equal to 5, which is the number of columns inside of this vector, inside of the matrix. In fact, that is we're going to state both of those facts as theorems. Both of them are pretty substantial theorems. So we have the first one. It's our new definition of the rank of a matrix, and it's also a theorem. So for any matrix A, the dimension of the row space of A is equal to the dimension of the column space of A. They have the same dimension. For that reason, okay, and we call that number the rank of A. It's the number of, remember before we had rank was the number of leading variables in the reduced row echelon form of a matrix, of a coefficient matrix for a linear system. Number of leading variables or number of leading entries. That number we called the rank. It turns out that that is the same as the dimension of the row space of A, and that will always be the same as the dimension of the column space of A. So it earns the name rank of A. For that reason, by the way, that means if you take the transpose of a matrix, then its rows become its columns, but the number of leading variables when you do the reduced row echelon form will stay the same. And so we have a nice corollary to that theorem, which is that the rank of a matrix is equal to the rank of its transpose. Okay, and now we come to the shining star of our course, the Rank-Nullity theorem. You're going to hear a lot of, if you spend any time around math people, which, I mean, if you're taking linear algebra, you can't really avoid it, I guess, but usually I don't recommend. And you start talking to them about the Rank-Nullity theorem, they'll generally agree this is one of the most, at the very least, it's one of the most convenient theorems in our subject, but also like one of the most beautiful. So let me just tell you, the nullity is the dimension of the null space. That's the definition that we give it. But the rank-nullity theorem says if A is an n by n matrix, then the rank plus the nullity is equal to the number of columns. That's it. The rank of A plus the nullity of A is equal to the number of columns. So in our example before, the rank plus the nullity is equal to 5. But notice this is also the rank plus the nullity is equal to 5. Yeah? So we'll give an example of how convenient this theorem is. Compute the nullity for each of these two matrices. Okay, well, notice these columns are clearly linearly independent. One is not a multiple of the other one, which means that the dimension of the column space is 2, which means that the rank is 2. Rank of n is equal to 2. But there are also two columns, so n equals 2. So the nullity is equal to 0 because 2 plus 0 equals 2. Convenient. I didn't have to solve a system of linear equations. I didn't have to like row reduce anything. Just had to like count. Okay. There's no so let's do it for this one. There's no obvious linear independence or dependence or whatever, so we will have to do a bit of row reduction. But if you just subtract, if you go and pivot around this 2, you'll get well, let's do it. We'll just do it. You'll see this is not so bad. So pivoting around that 2, I'm just gonna we know what row operations. Subtract 2 row 1 from row 2 and subtract row 1 from row 3. You'll get 2, -1, -2, -1, 0, 2, 1, 3, and 0, 6, sorry, we're subtracting 0, 1 from this, oh, okay, so +3 and +9, right? Subtract row 1 from row 3, like this. And then notice this row is 3 times the row above it. So subtracting 3 row 2 from row 3 will give us a row of zeros. 2, -1, -2, -1, 0, 2, 1, 3, 0, 0, 0, 0. A row of all zeros. Well, okay, so now what is the rank of this matrix? That's the dimension of the row space, also known as the dimension of the column space. The dimension of the row space is 2. So the rank of n is 2. Number of columns is 4. So the nullity of n is equal to 2 because 2 plus 2 is 4. Again, very, very simple computations. But remember that the nullity is the dimension of the null space. And the null space is remember when we computed it, we had to like solve the homogeneous system where this matrix is the coefficient matrix, right? So apparently that's telling us that there are 2 free variables when you go and do that. But all we had to do was just figure out the rank of the matrix. Now, let me tell you, we have some really, so this is the fundamental theorem for invertible matrices. You will often hear an invertible matrix described as full rank. A full rank matrix is one where the rank is equal to n. And in fact, that's the very first new characterization. So this is the fundamental theorem for invertible matrices, version 2. If you notice, the first 5 things on this list are the same ones that we had in the last video. But moving forward, let's just investigate what new things we have. So remember, A is an n by n square matrix, and it says the following are equivalent. We had these first 5 things that are equivalent to A being an invertible matrix. The newest thing to that is that the rank of A is n. In other words, it row reduces to the identity, but we already knew that one. Every row contains a leading entry in row echelon form, right? Or another way of saying it is that the dimension of the row space or the dimension of the column space is all of n, like all is n. Okay, that's the same as saying that the nullity of A is 0, or that there are no free variables in the homogeneous system whose coefficient matrix is A. This is the same as saying that the columns of A are linearly independent, or that the columns of A span all of Rn. But both of those things tell you that the columns of A form a basis for Rn. And all three of those things are also true about the rows of A. So there you go, 13 equivalent conditions for A to be an invertible matrix. Again, a lot of these things cut the amount of work that we have to do in one way or another way, because like, oh, I have to show some matrix is invertible, but like, look, its columns form a basis for Rn or something like that, right? Well, it's invertible because it's one of these 13 equivalent conditions, right? So I'm not going to go and prove this, but it's more of the same circular chain of implications that we had before. Instead, I want to talk about one last thing that returns us to the original questions that we were asking about, like what is a subspace though? So we have a gnarly definition. We're going to talk about the coordinates of a vector with respect to a basis. So, okay, here's the setup. S is a subspace of Rn. We have this script B, which is the set V1 up to Vk, which is a basis for the subspace S. Apparently, S is a k-dimensional subspace, right? Because there are k vectors in this basis, and the number of vectors in every single basis is the same. And that's the dimension of that basis. So S is a k-dimensional subspace of Rn with basis B. And then we just let V be some vector in S. Now, if V is a vector in S, then it can be written as a linear combination of the basis vectors because those basis vectors span all of S. I've put the word unique in parentheses here. It's not obvious that there's only one way to write the vector V as a linear combination of these other vectors. That's actually a theorem. A theorem says that if you have a basis for a subspace and a vector inside that subspace, then there's only one way to write that vector as a linear combination of your basis vectors. That proof involves the fundamental theorem of invertible matrices, but it's also not worth diving into for right now. Instead, I want to focus more on this definition. We call the coefficients of the linear combination, so C1 up through CK, the coordinates of V with respect to the basis B. We also write them as a column vector, and we call it V with an arrow on top and a B as a subscript in brackets. Very confusing notation, but we will come back to this later on when we start talking about linear transformations and things like that. Anyway, this column vector gets a name. It's called the coordinate vector of V with respect to B, right? So let me give you an example of this thing. If I had the vector 1, 2, 3, well, this is 1 times 1, 0, 0, plus 2 times 0, 1, 0, plus 3 times 0, 0, 1. This is how you would write the vector V, or the vector 1, 2, 3, with respect to the standard basis in Rn. So in other words, the coefficients of the linear combination are 1, 2, and 3. And if we were to write them as a column vector, we have V is this thing, then V with respect to 1, 0, 0, 0, 1, 0, 0, 0, 1, the standard basis, is the thing itself. That's why we call it the standard basis. It's the one basis where the coordinates of the vector are the same as the entries of the vector. That's not always true. And in fact, let's take a look at this example that we had. We talked about this earlier. We said that this vector W, which lived inside the span of these two vectors, 3, 1, 3, negative 1, 5, and 2, 1, 3, well, we said that that one was a linear combination, and we kind of worked it out. We said that it was 2 times the first one minus 3 times the second one. So that is to say W equals 3 times, 2 times 3 negative 1, 5 minus 3 times 2, 1, 3. Then the coordinate vector of W with respect to B, where this is, this is the basis B, is just the column vector 2, negative 3. Notice two-dimensional because S is a two-dimensional subspace of R3. Yeah. Okay. Good, and that's a good place to stop for this video. So we kind of blew through the rank-nullity theorem and the fundamental theorem of invertible matrices. I'm telling you, these are highlights for our class. So definitely, if you're going to read a section in the book, this is the section to read. It's a bunch of results that are just like, well, we're going to keep referring back to them as we move forward through the rest of our class. But anyway, that's the end of this video, and I will see you all in the next one.